So today we're starting chapter 3, and chapter 3 is all about exponential and logarithmic functions. And today we're going to start in section 3.1, and it's all about exponential functions. The first thing we need to remind ourselves is what is an exponential function. Remember, it's a function where the x is in the exponent, and the base of the exponential has to be something other than 1. So there's all examples there of different exponential functions and then things that are not exponential functions. Remember that the number, for example, the 2 here is the base. That will be an exponential base 2. And those can change given different exponentials. The first objective is just evaluating an exponential function. This is basically knowing how to punch these into our calculator. And in order to practice this, we're going to use a little word problem. This has to do with the Challenger. It's a space shuttle that had exploded on its launch. So here's our question. The morning the Challenger was launched, the temperature was 31 degrees colder than any previous experience. And we want to find the number of O-rings expected to fail at this temperature. So here's our given function where x is the temperature, and we're going to find the number of failed O-rings. So since the temperature was 31 degrees, we're going to go ahead and put the 31 in for the x. I want you to pause your video and punch 31 in for the x and use your calculator and see if you can come up with the answer. Hopefully, you decided that the number of failed O-rings was somewhere around 3.8. So we could say 4 O-rings failed, and that's why this space shuttle exploded. The second objective deals with the graphs. Now, if you look, I have graphs of a bunch of different exponential functions here. The base is changing, so here's a base of 1.5, here's a base of 2, here's a base of 3. Over on the other side, you can see there's our fractional bases, and notice how their graphs change. They're decreasing instead of increasing. And there's some things that all of these equations have in common. I want you to look at the graphs here and try to find some things they all have the same. What do all the graphs have the same? And I want you to put those together to decide the characteristics of the graphs of exponential functions. Now, once you've come up with some characteristics, I want you to go ahead and you'll be putting those answers into your Google form. So here's your free response question for your Google form today. What are some characteristics of the graphs of exponential functions? So now we're actually going to do some graphing, and we are going to use our transformations to graph these exponentials. Let's go ahead and look at the first one here. 3 to the x plus 1. Now, the first thing you should notice is that the parent graph we're going to use is 3 to the x. Let's take a minute and just think about what 3 to the x would look like based on the previous slide. Hopefully you decided that all of those graphs had an asymptote along the x-axis, and they all also crossed the point 0, 1, because 3 to the 0 would be 1. Now if x is 1, 3 to the x would be 3. So 1, 3 is the other main point there for our 3 to the x graph. Now we could connect those and sketch in our exponential graph. But that's not the graph I want. I want 3 to the x plus 1. Now what does that plus 1 next to the x mean? Hopefully you're deciding that it's moving this graph left 1 unit. So now all we have to do is go over and move everything on our blue graph left 1 unit. When I move my asymptote to the left, it's not going to change. It's going to stay where it is, really, because it's a line, a horizontal line. I'm going to move each of those points left 1 unit, and I can go ahead and sketch in that graph. And there's f of x equals 3 to the x plus 1. Let's take a look at another one. F of x equals 2 to the x minus 3. Again, the first thing is to think about the parent. The parent graph in this case would be 2 to the x. Now, how is that different from 3 to the x? They have the same horizontal asymptote. They still cross the point 0, 1. But now when I go over 1, I'm only going up 2 units. Now let's look at the transformation we're making. We have a minus 3 to the whole equation. Hopefully you're deciding that that's moving this graph down 3 units. So now we'll go over to the graph and just bump everything down 3 units. That means my horizontal asymptote is going down here to negative 3. And let's move each of these x's down 3 units. And we can sketch our graph in. And there's 2 to the x minus 3. Let's go ahead and try just one more. Now I'm actually going to change this equation. Let's change this. Nope, not clone it. Let's graph f of x equals negative 1/2 to the x minus 1. So the first thing we have to think about is the parent. Now hopefully you're deciding that the parent is y equals 1/2 to the x. Now, just like the other two, the parent would still have that horizontal asymptote and the point 0, 1. But now when I go over 1, I'm only going up 1/2. This is a decreasing graph. Now I like to also plot the reciprocal of that at negative 1, so we can go to negative 1 and up to 2. If you take the reciprocal of 1/2, you get 2. And that just helps give me a little bit better of a shape. Now that we have the parent, let's talk about the transformations. We've got that minus 1. That's moving the graph to the right. So there's our horizontal. And we have this negative in front of the entire equation. Hopefully you remember from chapter 1 that that's flipping the graph over the x-axis. So we're going to move everything to the right one and flip it over the x-axis. Now our asymptote's not going to change. When I move it to the right and flip it, it stays where it is. All these other points have to go right 1. So we'll move that top one right 1, and then they're going to flip down below because they're going to flip over the x-axis. Right 1 and flip, right 1 and flip. And we get our exponential function. And notice that now it's flipped into the lower part of the graph because of the negative in the front. Now, sometimes we're going to have a special exponential, and this is called e to the x. And this is our base e exponential function, and that's what objective 3 is about. Now, base e just means the number 2.71828183, and it keeps going on forever. E is just like pi. It's a special number. If you look at your calculator, you do have an e to the x button in your calculator. Go ahead and grab it and punch in e to the 1. Hopefully you'll see that you get that number there. So it's just like pi. It's a special number in math. It's what we call the natural exponential function. The reason is that this ratio happens very often in nature, and so it got a special name, e. So whenever you see something like e to the x, don't get confused. It just means 2.71 to the x. It's the same thing. It just goes on forever like pi, so that's why it gets a special name, e. Let's take a look at a word problem. The population of a small Polynesian island can be modeled by the equation f of x equals 8e to the point 8x. Now we're going to use this equation to answer the questions below, and we're going to round our answers to the nearest integer. The first question wants to know how many people started on the island. So when x is 0, how many people were there? The second question is how many people will be on the island 10 years later? So when x is 10, how many people will there be? Go ahead ahead and pause your video and see if you can come up with these answers. Hopefully, you came up with 8 people for the first one and 23,848 for the second. We're going to take a look at our last objective for today, and these deal with compound interest formulas. Now, this is a very useful objective in the real world because this has to deal with money in banks. Now, the way it works is when you bring your money, say, to a bank and you put it in a savings account, they're going to calculate interest. You're going to earn money off of the money you put in. Now, they're going to calculate this interest a certain number of times per year. That's the compounds. That's what compounding means. How many times are they calculating this interest? Now, there's 2 different formulas we can use to calculate interest. The first one is compounding per year. The second one is compounding continuously. And it all depends on the situation you have, which formula you'll use. Now, for both these formulas, the P is going to be your initial value. How much you're putting in. The R is going to be your rate per year, your yearly rate. And you're going to write this as a decimal. It's going to be usually given to you in a percent, but you're going to write it as a decimal. The N is going to be the number of compounds per year. For example, if it's compounding monthly, it would be 12. Compounding daily, 365. Compounding quarterly, that would be 4 times. And finally, the T is going to be your number of years. Now notice that in the compounding continuous formula, we have that E involved there. We like to call that one the PERT formula, P-E to the R-T. And based on your question will depend on which formula you would use. Now, just to give you an idea, here's a part of the website from Wells Fargo that I pulled up, and it has to deal with a savings account there, their money market savings. And if you look down here towards the bottom, you can see that for this account, they're compounding daily. And the annual percent that you would get is 0.05. So in terms of the word problem, if we put this information into a word problem, the compounding daily would be 365 for our N. Our rate would be 0.0005 as a decimal. The time would depend on how many years, and again, the P would be how much you're putting in. Notice in this case, your P would have to be at least $100. So you can see this information is very useful in real-world situations. Let's put it all together, though, in an example. We're going to be investing $8,000 over 6 years, and we're going to choose between 2 accounts. The first one is going to give us 7% per year, compounded monthly. The second one would give us 6.85% per year, compounded continuously. And we want to decide which is better. So we're going to use each of those formulas. Now here's the first one again. A equals P times 1 plus R over N to the NT. Now in this case, our P is 8,000. That's how much we're starting with. Our time is 6 years. Our rate is 7%, and monthly is going to give us our N. So putting that all together, we'd get 8,000 times 1 plus. Now our rate as a decimal, 0.07 over. Now compounding monthly, monthly means it's going to happen 12 times a year, times 12 times to the 12 times 6, NT. Go ahead and use your calculator, pause your video, and try to see how much that will equal. Hopefully, you got somewhere around $12,131.86. So our $8,000 in 6 years is turning into $12,000. Let's do the same thing, only now we're compounding continuously. So now we have to use that other formula, PE to the RT. Our P doesn't change. Our rate, though, does, 6.85%. And our T is still 6 years. Go ahead and pause your video and see if you can come up with amount. Hopefully you got somewhere around $12,066. Now your amounts might be a little bit different based on how your rounding happens, but you can see clearly that the better investment would be to use the first account. I'm going to give you a question like this to try. This will be your multiple choice question for your Google form. So I want you to go ahead and answer this, and then you'll put your answers to this question and your free response question into that form, and we will take a look at these things more tomorrow.